Hi, most welcome to Dr. Acharya Academy. Today, I'll discuss on the topic periodic trends with respect to ionization enthalpy. This topic has been taken from the NCERT Chemistry Class 11 books. It is the part 1 unit number 3. Today's class number is 057. Quantitative measure of the tendency of an element to lose electron is given by its ionization enthalpy. This ionization enthalpy represents the energy required to remove an electron from an isolated gaseous atom considered X in its ground state. This is the equation. This X is a gaseous atom in bracket, that's a small g is there, and the energy required, which is the ionization enthalpy, to remove this electron and to get the X plus ion, that means X plus cation in its gaseous state. So this is the first ionization enthalpy because the first one electron is removed by the energy as per the ionization enthalpy. So this is the first ionization enthalpy for an element X, and it generally written by the enthalpy change delta IH. Delta subscript small I and capital letter H. H capital letter denotes for the enthalpy. Again, we learned in details during the discussion in the thermodynamics chapter. The ionization enthalpy is expressed in units of kilojoule per mole. The second ionization enthalpy. Second ionization enthalpy means the second electron will be removed from this X plus cation in its gaseous state. So equation will be like that. X plus in its gaseous state will convert to the X2 plus in its gaseous state plus electron. So the second ionization enthalpy can be defined as the energy required to remove the second most loosely bound electron, and it is the energy required to carry out the reaction as per this equation. Energy is always required to remove electrons from an atom, and hence the ionization enthalpy are always positive. The second ionization enthalpy will be higher than the first ionization enthalpy. Why? Because this second electron is more difficult to remove from the singly positive charge ion than from a neutral atom to remove the first electron. So in the same way, the third ionization enthalpy will be higher than the second ionization enthalpy, and so on. Because for removing the third electron from the doubly positive charge gaseous ion, it is more difficult than the electron removed from the single positive charge gaseous atom. So the term ionization enthalpy is taken as the first ionization enthalpy. That means if it is not mentioned that second and third ionization enthalpy, then we always will consider ionization enthalpy means the first ionization enthalpy. In this figure, you see the variation of the first ionization enthalpies with atomic number for elements 1 to 60. Here you can see the maxima. These all are the maxima. In these maxima, all noble gas atom is sitting in each maxima. So the maxima can be found at the noble gas which have closed electron shells and very stable electron configuration. So these noble gas atoms has very stable electron configuration, so it is very difficult to remove electron from its outer shells. And you can see in the minima, these all are the minima. In this minima, all group 1 elements is there. See, lithium, sodium, potassium, etc. So these minima occur at the alkali metals for the group 1 elements, and their low ionization enthalpies can be correlated with their high reactivity. From the previous class, we understood that the alkali metals is highly reactive. That means these elements, atoms, always ready to release electrons to show its high reactivity. Ionization enthalpy and atomic radius are closely related properties. The first ionization enthalpy of elements having atomic numbers up to 60 is plotted here. See, this is the group 1 elements, and this is the second period in this ascending order in this line. So two trends are noticed. The first ionization enthalpy generally increases as we go across a period. This is the period, second period, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. This is the second period. So across the period, is first ionization energy, this y-axis is the first ionization enthalpy and is increased. But for group, it decreases. That means the first ionization enthalpy decreases as we descend in a group, That means in a group, if you go from top to down, then first ionization enthalpy will be decreased. To understand these trends, we have to consider two factors. The first factor is the attraction of electrons towards the nucleus, and second factor, the repulsion of electrons from each other. The effective nuclear charge experienced by a valence electron in an atom will be less than the actual charge on the nucleus because of shielding or screening of the valence electrons from the nucleus by the intervening core electrons. The shielding effect I already discussed in the previous unit number 2. And these two factors we have to remember to explain why the ionization enthalpy increased along the period and why the ionization enthalpy is decreased across the group, that means descending the group. So example, the 2s electron in lithium is shielded from the nucleus by the inner core of 1s electrons. And what is the result? The result is the valence electron experience a net positive charge which is less, because due to the 1s electron shielding effect, 2s electron will feel less positive charge than the actual charge of +3. In general, shielding is effective when the orbitals in the inner shell are completely filled. This situation occurs in the case of alkali metals when have single outermost ns electrons preceded by a noble gas electronic configuration. When we move from lithium to fluorine across the second period, I already showed the figure. Successive electrons are added to orbitals in the same principal quantum level, and the shielding of the nuclear charge by the inner core of electrons does not increase very much to compensate for the increased attraction of the electron to the nucleus. Thus, across a period, increasing nuclear charge outweighed the shielding. Consequently, the outermost electrons are held more and more tightly, and the ionization enthalpy increase across a period. So now you understand that why ionization enthalpy is increased across a period. That means in a period, from left side element, if you go the right side element, then ionization enthalpy will be increased. Now for group, as you go down in a group, I already discussed that as you go down a group, then ionization enthalpy will be decreased. Why? The outermost electron being increasingly further from the nucleus. Go down a group, then new shell is entering, new outer shell is entering. So this outer shell is further, that means it has more distance from the nucleus than the element in a group just above of this particular element. So there is an increased shielding of the nuclear charge by electrons in the inner levels. In this case, what will happen? Increase in shielding outweighed the increasing nuclear charge. When I talk about the period, then it is the reverse case. The increasing nuclear charge outweighed the increase in shielding effect, But for the group, increase in shielding outweighed the increase in nuclear charge. And what will happen? The removal of the outermost electron requires less energy down a group. Again, you can see this figure. So this figure A, you will also notice that the first ionization enthalpy of boron, here a little bit anomaly is there. You see the along a period, first lithium, then beryllium. For this case, the ionization enthalpy increased, but for boron, it is little bit less. It's first ionization enthalpy and beryllium. Why it will happen? When you consider the same principal quantum level, because the along the period, all outer shell have the same principal quantum level, because same outer shell, and S electron is attracted to the nucleus more than a p electron. So what will happen? In beryllium, the electron removed during the ionization is an S electron, because the thing is that its electronic configuration, outer shell electronic configuration is 2s2, but for boron, outer shell configuration 2s2 2p1. So in beryllium, the electron removed during the ionization is an S electron, whereas for electron removed during ionization of boron, this is the p electron. For I told, for boron, it is the outer shell electronic configuration is 2s2 2p1. So this 2p1, from it one electron will be removed. But for beryllium, it is the 2s2 outer shell configuration. So one electron removed, it is from the s orbitals. The penetration of a 2s electron to the nucleus is more than that of a 2p electron, and hence the 2p electron of boron is more shielded from the nucleus by the inner core of electrons than the 2s electrons of beryllium. So it is easier to remove the 2p electron from boron compared to the removal of a 2s electrons from beryllium. And thus the boron has a smaller first ionization enthalpy than beryllium. Another anomaly is there. You can see here nitrogen and oxygen. Though oxygen sit in the periodic table right side in the same period, but oxygen atom has the less first ionization energy. This arises because in the nitrogen atom, 2p electrons reside in different atomic orbitals, that means Hundschul, whereas in the oxygen atom, 2 of the 4 2p electrons must occupy the same 2p orbital, resulting in an increased electron-electron repulsion. So for nitrogen atoms, these 2p orbitals, electrons, electron repulsion is happen. So what will happen? It is easier to remove the fourth 2p electron from oxygen than it is to remove one of the 3 2p electrons from nitrogen. So I'll explain in details that N, you know its electronic configuration is 2s2, 2px1, 2py1, 2pz1. And for oxygen atom, the electron configuration is 2s2, 2px2, 2py1, and 2pz1. So for oxygen, whatever the electron will be removed, first electron, that is from 2px2, because the 2px2, it is paired, that means electron-electron, due to electron-electron repulsion, this electron from oxygen atom can be easily removed. Now, we'll see one problem which can be helpful for your exam. What is the problem? The first ionization enthalpy values of the third period elements sodium, magnesium, silicon are respectively 496, 737 and 786 kilojoule per mole. Predict whether the first ionization enthalpy value for aluminium L will be more close to 575 or 760 kilojoule per mole. Justify your answer. What is the solution? It will be more close to 575 kilojoule per mole, because the value for aluminium should be lower than that of magnesium because of effective shielding of 2p electrons from the nucleus by 3s electrons. I hope that you understand this topic very clearly, and the periodicity of the ionization enthalpy. You can check also the podcast of Dr. Acharya Academy for honors degree chemistry level education. Thank you so much for watching this class.